The purpose of this video is to learn how to use the IUPAC system, International Union of Pure and Applied Chemistry, to name molecules that have ketone functional groups. As a reminder, a ketone group has a carbonyl, that's a carbon-oxygen double bond, like I'm highlighting here at the bottom of your screen, directly connected to two carbon atoms here and here. Beyond that, there can be whatever other groups we want, but we absolutely, in order for the molecule to be referred to as a ketone, has to have carbon atoms flanking the carbonyl group on both sides. Otherwise, the molecule would represent a different functional group, such as an aldehyde, an ester, a carboxylic acid, or something else entirely. Let's go ahead and take a closer look at how to go about naming ketones using the IUPAC system. We will see many parallels between naming ketones using the IUPAC system and other classes of molecules that we previously looked at. In particular, if you're feeling rusty on nomenclature in general, viewing my video number 310 will be very useful to get back up to speed on the generalities of nomenclature. So we're going to focus here in this video specifically on IUPAC naming of ketone molecules. And we're going to walk through the rules for naming ketones, and then we will go about applying these rules towards some example problems. First things first, when we are naming ketones, much like when we're naming other functional groups, we are tasked with finding the longest carbon chain, and that longest carbon chain needs to contain the carbon that has the carbonyl group of the ketone. So find the longest carbon chain that contains the ketone group. And that ketone group is generally going to be what we use as our determinant for where we start numbering the longest carbon chain. So generally, if a ketone group is the only functional group in the molecule, meaning the other branches coming off of the parent chain are alkyl groups, we will number from the end closer to the ketone group when we are numbering that parent chain. So we'd start numbering with carbon number 1 being the carbon that is closer to the ketone group. Now there is a hierarchy for how to number, and you may occasionally find this hierarchy useful. This would be what you would need to apply if you were in a situation where you had multiple functional groups present within the molecule. The hierarchy is this. If you have an aldehyde group in your molecule, the aldehyde group is what is going to dictate where the parent chain starts and what's contained in the parent chain. You would find the longest carbon chain relative to the aldehyde group being at one end of that chain. Next up in the hierarchy of functional groups that we've learned so far are ketones. So if you have an aldehyde and a ketone group in the same molecule, you would find the longest carbon chain and start numbering relative to the aldehyde group, not relative to the ketone. Ketones outrank alcohols, so if you had a molecule that had both a ketone group and an alcohol group, you would find the longest carbon chain and number it relative to the ketone being closer to the end of that longest carbon chain. Carrying on, we have alkenes and alkynes that are lower ranked when determining how to go about assigning priority than any of the groups we've mentioned before. And then finally, at the bottom end of the spectrum are our alkyl groups, our halogen atoms, or halides, such as chlorine, bromine, fluorine, and iodine, and also ethers. All of those are tied at the bottom of our hierarchy. So when we are looking at a molecule, if a molecule has multiple functional groups, what you do to find which one is going to dictate the longest carbon chain and determine the parent name is you look through this list and find what is highest up on this hierarchy list. That's what's going to drive where you look for the longest carbon chain and what is going to be the main determinant of where the longest carbon chain is and where you start numbering from. With regard to ketones, if we determine that the ketone is the highest ranking of the hierarchy, which very commonly it will be because you'll notice it's second from the top of the functional groups that we've learned so far, what you will do is once you've found the longest carbon chain that contains the ketone, you're going to name that as the parent name. And to name the parent name of a ketone, you will take the corresponding alkane name, such as propane, delete the E from propane at the end, and change it to ONE for ketone. So the parent name follows the template of the alkane, where you would replace the alkane part with the indicator of how many carbon atoms are in that chain. So for instance, butanone would have 4 carbons in the chain, and somewhere along that chain it would be a ketone group. You do need to specify in that parent name where the carbonyl group is located, because unlike aldehydes, where the carbonyl group has to be at one end of the chain, specifically at carbon number 1 of the chain, instead with ketones, you would get different structural isomers, or constitutional isomers, as we may call them, by putting the carbonyl group at different positions of the chain. So when you name the parent name, you have to specify the number location of the carbonyl carbon within that chain, remembering from step 1 that you're going to number from the end closer to that carbonyl group of the ketone. So when we are specifying the parent name here and indicating the location of the carbonyl group, you can do that in one of 2 ways. You can do X alkenone, where X equals the location of the carbonyl group. So this X would be the carbon number, or the ketone group. Or you can alternatively call it alkane, XONE, to put that numerical location as close to the designator that the molecule is a ketone, that ONE. So either of those routes will work. Once you have specified the parent name and the location of that carbonyl group within the parent chain, the next step is to name and number the branches. And this step of naming and numbering the branches follows exactly the same template that we looked at in prior videos, such as video 310, where we introduced nomenclature. So when you're naming and numbering the branches, remember that you include those as prefixes that would come before the alkenone parent name, and those prefixes, or those branch names, are listed in alphabetical order at the front end of the name. And the numbering of these branches would be dictated by the numbering of the carbon chain that you used in step 1. Now that we've laid out these steps for determining the name of ketones, let's go ahead and apply that towards some example problems. Here we go. I'm going to zoom out a bit on this general information so that we can apply it towards some specific situations. So let's do an example problem here. I'm going to draw out a ketone molecule, and our task is going to be to go about determining the IUPAC name of this particular ketone molecule. So let's take a look at this structure. Now, as we take a look at the structure, we need to find first the longest carbon chain that contains the ketone group, or whatever the group is that's highest in this hierarchy here. As we look at our structure here, the only non-alkyl group we have in the molecule is this carbonyl group here that we recognize as part of a ketone group. And so therefore, out of this list, ketone is the highest ranked group, and therefore we're going to find the longest carbon chain that includes that ketone group, and we are going to start numbering that longest carbon chain from the end closest to the ketone group that is anchoring us. So let's go ahead and do that. We'll start from this end because this is the end closest to the carbonyl group of the ketone. There's our ketone group that I just highlighted in green. Following through, when we get to here, we have a branch point, and we could either choose to come this way, or we could come up through here and go here, or we could alternatively go to here. We're going to choose to come this way because this takes us the longer path than if we went this way, or that way for that matter. Coming this way, we would end up with 2 more carbons in our chain. Coming this way, we have the opportunity to do 3 more carbons. 3 is going to dominate over 2, so we come up to here. When we get to this point, we could either go up here or over here. Since these are both methyl groups, completely identical, it doesn't matter which one you choose. You will come up with the same IUPAC name one way or the other. So I go ahead and follow that to the end there. Now I'm going to number this. Remember, number from the end closer to the carbonyl group of the ketones, as the ketone is the most important in determining the nomenclature here. So we have a total of 8 carbons in our longest carbon chain. So the parent name, if this were just an alkane, would be octane. But keeping in mind that there is that ketone group in there, it becomes octanone. And we have to specify where the carbonyl group is. It's at position 3, so octan 3-one. Or you could alternatively have referred to this as 3-octanone. That would be totally appropriate as well, although the most current IUPAC rules suggest using this octan 3-one designation with the numerical location of the group right before the group designator -one. So that takes care of everything that is highlighted in green within our molecule. But we have some aspects of the structure that we have not yet identified, namely this methyl group right here at position 7, and then this group here, which we'd refer to as our isopropyl group, because an isopropyl group is a 3-carbon chain where that carbon in the middle is what connects to the parent, to the rest of the molecule. I'm going to sketch in the names of these branches that we've highlighted in pink. So at position 5 of our parent chain, we had an isopropyl group, so I'm going to go ahead and name that isopropyl. At position 7, we had a methyl group, so I'm going to name that 7-methyl. Now to put those into the name here, they come in listed as prefixes by alphabetical order. I as in iso comes before M as in methyl, and so therefore 5-isopropyl is going to come first in our name for this molecule. So I'm going to write that in as 5-isopropyl, 7-methyl, octan 3-one, and since the word methyl and octane have no numbers needed listed in between those two words can run directly together, no hyphen or anything else needed. If you are using the other designation of 3-octanone, you would need to put a dash between the word methyl and the number 3 because we always separate numbers from letters using dashes. All right, so with that problem handled, let's go ahead and take a look at another possible molecule here. In this one, I'm going to use a ring. Rings are something that, for some reason, people notoriously don't really care for. So in this structure, as we look at it, the highest ranking functional group for determining our parent is the ketone group again, because all we have here are our alkyl group and our ketone that we recognize here. So the parent name is going to be based on the ketone. And in this case, we don't have a carbon chain, so that's not really relevant. Instead, what we do is we designate the parent based on the ring that we have present by using the term cyclo to specify that number of carbon atoms that are in the ring. In this case, we have a hexagon or 6 carbon atoms in the ring. And so the parent name for this molecule becomes cyclo to indicate the atoms are connected into a ring rather than a chain, and then 6 carbon atoms, so it's hexanone. And it's assumed here that the carbonyl group must be at carbon number 1 of the ring, because since we don't have a chain here, instead we have a continuous ring, that allows us to always put the carbonyl group at position number 1 by default. So we don't need to say here 1-cyclohexanone. When they're in a ring, it is implied that position 1 of the ring is going to be the carbonyl group of the ketone, since the ketone group is the highest ranking out of our hierarchy. We will number the ring based on the relative position of the next branch coming off of the ring compared to where the carbonyl group is. And we want to take the shortest path around to get to the next branch. So we number in this case clockwise, because that would put the ethyl branch here in black, which I'm highlighting now, at position 3, whereas if we went the other way around, the ethyl branch would instead be at position number 4, because we go 1, 2, 3, 4, 5. Oh, my bad. It would actually be at position 5. So 1, 2, 3, 4, 5. That would definitely be the long way around, so that's not the correct way to do it. Instead, we go this way, and that puts the ethyl branch at position number 3. So number the path to take the shortest distance to reach the next branch away from the carbonyl group. So that's at position 3 then, we have our ethyl group. And we do need to specify where that ethyl group is, because depending on where the ethyl group is around the ring, that would create different constitutional or different structural isomers, as we could call them. If the ethyl branch were instead at position 2 or instead at position 4, we would have different IUPAC names for those molecules, and they would represent different constitutional isomers. So the full name for this molecule is 3-ethyl cyclohexanone, keeping in mind as the key for solving this problem that it is essential you recognize that the carbonyl group of a ring will always be at position 1, assuming it's the highest ranking group out of this hierarchy, and then you number going in the direction to get you as fast as possible to the next branch away from that carbonyl group that anchors the molecule or that forms the basis of the parent name, in other words. Let's do one more example of naming these types of molecules. In this example, what I'm going to do is highlight how to go about naming molecules when, rather than having just one of these functional groups from the hierarchy present, you have multiple. In this molecule, as we take our initial assessment, you should notice that there are 3 different functional groups that we need to contend. We have the aldehyde group right here, a ketone group over here because this carbonyl has a carbon on both sides directly bonded, and then we also have this alcohol group here. So how do we go about doing this? Well, first off, we're going to look at the hierarchy here and pick what comes out of the hierarchy highest. That is going to dictate where we find our parent chain and where we start numbering that parent chain. Of the 3 groups, aldehyde, ketone, and alcohol, we see that aldehyde is highest in the hierarchy, and so that's going to determine where we start finding our longest carbon chain. So our longest carbon chain is going to start at the carbon that I've highlighted in green here. That's going to form the basis of the parent name, so I'm going to highlight the carbonyl group and the hydrogen there because the parent name will be based on the aldehyde. Coming through the chain, we take our longest pathway through. When we get to this point, we have 2 possibilities. We could either go up through here to get to a 3-carbon chain, or we could come down through here to get to a longer carbon chain. Take the longer path. So we take the longer path through here, coming on through to the very end of that chain. That chain is going to be our parent chain, which we start numbering from the end closer to the highest ranking group in that chain. That's our aldehyde group. And numbering from there, number 1 is our aldehyde carbon, number 2, 3, 4, 5, 6, and 7. So based on the fact that there are 7 carbons in our longest carbon chain, the parent name of this is going to be based on heptane because heptane was our 7-carbon alkane. Now, since the molecule has an aldehyde group as the highest ranking of the different groups that are present here, the parent name is going to adopt the aldehyde designation. The aldehyde designation was Al as the suffix to indicate the molecule was an aldehyde. So, in this, we would refer to this chain as heptan-al with the Al suffix denoting that there is an aldehyde group. We do not need to call this one heptanal. It is implied that the aldehyde group always has to be at carbon number 1 because it always has to be at the end of the chain. So from there, what we will do is, much like we've done before, with the parent name filled in now as the aldehyde parent name because the aldehyde was a higher ranking group than the ketone, we now will name the other groups that we haven't yet highlighted here. In other words, the groups that weren't part of the parent chain, we name as branches. So in red highlighter, we have a 3-carbon chain here. That is 1, 2, 3 carbons that we haven't accounted for in our parent green chain. 3 carbons that are just a straight chain is referred to as a propyl group. So we would call this a 3-propyl group because it is at position 3 of the parent chain that it branches off. At position 5, here's some totally new information for you that we haven't yet discussed. If a carbonyl group of a ketone is a branch rather than being incorporated into the parent name, then it is referred to as an oxo group. So this would be referred to as a 5-oxo group. Oxo refers to a carbonyl branch. And that is a good term to keep in mind that may become useful later on. So in cases where the ketone does not form the parent name because the ketone is not the highest ranking in this hierarchy, the ketone group is referred to as a branch, and the specific name of a ketone branch is an oxo branch. So that would be a 5-oxo group because it comes off of the parent chain in green at the 5 position. And then at position 6, in an earlier segment we mentioned this, but it's worth repeating here, an alcohol group, when it's a branch rather than the parent, is referred to as a hydroxy group. So this would be a 6-hydroxy group. Now, we list those prefixes in order, alphabetical order to be specific, in front of the name heptanal. Heptanal was our parent name due to the chain that we came up with in green. Now, listing these in alphabetical order, hydroxy comes before oxo, and oxo comes before propyl. So I'm going to list those in alphabetical order here, starting with 6-hydroxy. 5-oxo-3-propyl. And the word propyl runs directly into the word heptanal. No space between those two words, propyl and heptanal, because there is no number there, so we don't need any dashes, we don't need any spaces, anything like that. So our full, complete IUPAC name for this molecule is what I'm highlighting in yellow here for this particular molecule. That incorporates all of the branches, which we've highlighted in pink and listed in red down here in the name, and the parent chain, which we've listed in green and written out here in green as well. So now with this information in mind, you should be comfortable with naming a variety of linear and cyclic ketone molecules and molecules that have not only a ketone functional group, but also other functional groups listed here as well.